Okay. This video is going to take care of some homework solutions from section 8.4. All right. Section 8.4 is the other convergence tests. Here we get the alternating series test and we get the ratio test. All right, so I'm going to just do some problems here from the homework. I'll start with number 8. 8 says test the series for convergence or divergence, and we get this. Right, here's what we get for number 8. We get sigma n equals 1 to infinity minus 1 to the n divided by the root of n cubed plus 2. Okay. So this is clearly an alternating series. It has a -1 to the n here. Now, the alternating series test is one of those tests which, once we know how to use it, as long as we don't abuse it, most people have nothing but joy for the alternating series test, right? They like the alternating series test. It says, right? It says if you have an alternating series, all you have to do is satisfy 2 conditions, right? 2 conditions. You've got to be decreasing, and by decreasing, we mean b sub n, right? The positive factor. In other words, we ignore the -1 to the power. Right? That has nothing to do with showing it's decreasing. So we have to show it's decreasing. And then 2, we've got to show that the limit as n goes to infinity of b sub n, same b sub n up here, equals 0. That's it. That's it. That's the whole thing. So for most of us, the hard part or the more difficult part is showing that it's decreasing, right? Showing that it's decreasing. We can do this usually by taking a derivative and trying to show that the derivative is negative, and therefore we're done. Now, sometimes people don't like to take the derivative. I'm gonna do this 2 ways, right? We're gonna take care of our decreasing question right here. And we're just gonna go ahead and first do it with calculus. And to do it with calculus, we're gonna take the derivative. Okay, so we're gonna say f of x equals x over x cubed plus 2 to the 1/2, and we're gonna find f prime of x. So we take the denominator times the derivative of the numerator, right? We're gonna do the quotient rule, minus the numerator times the derivative of the denominator, which is going to be 1/2. That's going to come down. We're going to have x cubed plus 2 to the minus 1/2 times 3x squared, chain rule, divided by, now we square this, and that just gives me x cubed plus 2. Okay. Now we're in Calc 2. We're trying to show this is negative. You and I know this is always positive. When x is greater than or equal to 1. So I'm just going to ignore that from now on, because all we're worrying about is whether or not this is negative. So I'm just going to consider only the numerator, right? Because the denominator is always positive. So the only thing that's going to make this fraction negative is the numerator being negative. Now we're going to factor out an x cubed plus 2 to the minus 1/2. Here, that's going to leave me an x cubed plus 2 to the first. Minus from there, this is gone. And we have, right, we have 1/2 times 3, that's 3/2. X times x squared, that's x cubed. Again, I'm not going to write down the denominator. Now, what does that turn out to be? Well, this part now becomes part of the denominator. Again, it should be 3/2, but this part's right here. We're ignoring that. What's left on the top? We have x cubed minus 3/2 x cubed plus 2. Again, I'm going to ignore the denominator. Same reason that I ignored it above. And what do I have? I have minus 1/2 x cubed plus 2, which is going to be less than 0 when x is greater than or equal to 2. When I put a 1 in there, I'm going to get a positive number. But when I put a 2 in there, I'm going to get 8. Half of 8 is 4. Negative 4 plus 2, that's negative. When we say decreasing, this is what we mean. It's eventually going to be decreasing. It's not decreasing for the first term, but it's decreasing for every term after that. So the first term is going to be bigger than the second term. The second term is going to be bigger than the third term, etc. So it's decreasing, right? It goes down forever. Now, what do we have left to show? Oh, if we wanted to do this algebraically, I don't suggest this. And most of the time, this doesn't work. You could do this with algebra. Try to show that if you take the next term, it's smaller than this term. More often than not, we end up making algebra mistakes when we do that. I would not recommend that approach at all. I would not recommend that approach. So what are we left with? We have decreasing. Now we got to show the limit equals 0, right? Decreasing is done. We've got that. It's less than 0. So consider the limit as n goes to infinity of n over the square root of n cubed plus 2. Now, we had these problems back in Calc 1. And they told us to divide by the highest power of n in the denominator. But when we have this square root here, we need to think about this as n to the 3/2, don't we? Outside the radical. So what am I saying? I'm saying this. This is going to be the limit as n goes to infinity. Down here, this radical is now going to go like this, isn't it? I have an n cubed here. I'm going to divide by n cubed. I have a 2 here. I'm going to divide by n cubed. Now up here I have my n. Who am I going to divide by? I don't divide by n cubed because that n cubed is under this radical. That's actually n to the 3/2, isn't it? That's what that is. That's n to the 3/2. So when I bring n cubed out, right? When I bring n cubed out, what n did I put in here to make n cubed? It's n to the 6th, right? So this is going to be n to the 6th out here. Now what are we left with? We're left with the limit as n goes to infinity. We have 1 over n to the 5th in the top. Here we have the square root. We have 1 plus 2 over n cubed. And so this turns out to be 0 on the top. Here, this goes to 0, and I have the square root of 1, so I get 0. I've satisfied both conditions of the alternating series test, so therefore, this series converges by the alternating series test. All right. So that's number 8. Let me erase this. We'll take a look at 15 next. So what about number 15? 15 says, show the series is convergent. How many terms of the series do we need to add in order to find the sum to the indicated accuracy? Okay, so this is what we looked at in problem 33 of section 8.3, right? They want us to find a value of n that will allow us to get an indicated accuracy. And for problem 15, it's 0.00005, right? 0.00005. So we're going to be looking for a value of n, right, in problem 15, because it says first show its conversion. So we'll do that part first, right? So problem 15, we have sigma n equals 1 to infinity. We have -1 to the n plus 1 in the numerator, and down below we have n to the 6th. Okay. So what do we have to do? We've got to show that this is decreasing, right? Got to show that. Got to show it's decreasing. Now here, we can probably get by with using the algebra approach, right? Decreasing. So we got to show that the n plus first term is smaller than the nth term. Well, again, remember, we ignore the negative. So if we put an n plus 1 in here, we would have n plus 1 to the 6th. And we're wondering, is that really smaller than n to the 6th? Well, this denominator is smaller. Sorry, rephrase. This denominator is larger. N plus 1 is bigger than n. N plus 1 to the 6th, therefore, is bigger than n to the 6th. So since the denominator is bigger, the fraction is smaller, right? So we've got that. This is just done by inspection. Of course, if you wanted to take the derivative, you'd say f of x equals 1 over x to the 6th. F prime of x, of course, this is x to the -6, isn't it? So the derivative of this is -6 x to the -7, which is -6 over x to the 7th, which is always negative when x is greater than or equal to 1, which ours is. Because x to the 7th is always going to be positive. I know it's odd, but x is always positive. So when you raise a positive number to the 7th power, you're going to get a positive, and -6 is always negative. So we've got decreasing. Now we have to show the limit as n goes to infinity of 1 over n to the 6th equals 0. Well, again, that's done by inspection, right? There's no work here. This is 0. So this converges by the alternating series test. Now, in problem 15, it also says, find the value of n, right? Find the value of n so that the error is going to be less than. So we want our error to be less than 0.1, 2, 3, 4, 4 zeros and a 5. Okay, we want our error. Now, what do we know? We know that our error by the alternating series estimation theorem, right? Is less than, right? The error is less than the very next term. So we want to know what term is going to get us an error that's less than this. Well, it's whatever. We just need to know which term is going to be smaller than this. Right? If we put 1 in here, we get 1. If we put 2 in here, we get 1 over 2 to the 6th, right? So what can we do? We could, if we wanted to. We could just keep plugging numbers in with our calculator, right? We could ask our calculator, what's 1 over 2 to the 6th? And 1 over 2 to the 6th is 0.015, right? That's too big. And we could just keep plugging numbers in. Or we could solve, right? We could solve 1 over n to the 6th has to be less than 0.0005. Which means if we cross multiply, that both of these are positive. N's always positive, and the power's even, but either way. So if we cross multiply, we get 1 divided by 0.0005 has to be less than n to the 6th. And now, if we take the 6th root of both sides, and so if we ask our calculator what that is, right? If we ask our, I don't have a calculator on my phone, but I mean, we can get by doing that on the phone. So we have 1 divided by 0.12340 5. That's 20,000, right? So n's got to be greater than, so we raise that, and I don't have calculator, so I have to do to the 1/6 power. And we get 5.21. So n has to be greater than 5.21. Well, remember, n is 1, 2, 3, 4, 5, 6. So the first n greater than 5.21 is 6. So that's number 15. Let's go ahead and clear that off. Next, we'll take a look at 21. I'll look at 21. Remember, this is the alternating series and the ratio test. Maybe by the time we get to 21, we've gotten to a ratio test problem. Let's take a look and see. 21 says, determine whether the series is absolutely convergent. Now, when we're asked to determine if something is absolutely convergent, that's going to be the ratio test. The ratio test has a companion called the root test, which we don't cover, but they're the only two tests that give us absolute convergence. So remember, the ratio test, if we just remember the ratio test real quick, it says consider the limit as n approaches infinity of the absolute value of a sub n plus 1 over a sub n. And then we get, I don't remember the order your book does. What do they do first? Less than 1? Okay. So then we get 3 outcomes. We get less than 1, absolutely convergent. We get greater than 1, divergent. And we get equals 1, try another test. Because it's inconclusive. All right, so we have this problem. They ask us to show, it said in the instructions, again, just to remind you, 21, determine whether the series is absolutely convergent. So we're going to consider the limit as n goes to infinity. Now we're going to do the absolute value of a sub n plus 1 over a sub n. So we're going to put an n plus 1 over in here. So that's going to be negative 3 to the n plus 1 over n plus 1 cubed. And instead of dividing and making a complex fraction, I'm going to multiply by the reciprocal. So here I'm going to have n cubed. And then here I'm going to have negative 3 to the n. Now remember, negative 3 to the n plus 1. is one more -3 than -3 to the n. Right? I mean, -3 to the 8th and -3 to 1 less than that is just one -3. So this equals the limit as n goes to infinity. These people just give me a -3. Now I have an n cubed. And down here I have an n plus 1 cubed. When I take the absolute value of that, that 3 is going to become that -3 is just going to become 3. I can take that outside the limit. And now we don't really need the absolute value because n and n plus 1 are always positive because n goes 1, 2, 3, 4, 5. But we have n cubed over n plus 1 cubed. The greatest power in the numerator is 3. The greatest power in the denominator is 3. The limit equals the ratio of their leading coefficients. So we get 3 times 1, which is 3, which is greater than 1. So our series is divergent. Okay. So problem 21, I mean, we can look at the back. We're doing 8.4 here. 8.4 problem 21. Let's see how we did. It hopefully says, something that says divergent. Problem 21. Oh, determine whether the following series is absolutely convergent. Because in problem 21, it says no, it doesn't say divergent. It's definitely not absolutely convergent because we proved it's divergent. All right, so from 21, let's try 26. Same set of instructions for 26. They give us the series n equals 1 to infinity of n squared over 2 to the n. Okay, so we're going to do the ratio test again. So this is going to be the limit as n approaches infinity, the absolute value of n plus 1 squared, right? Because we're doing, remember, a sub n plus 1 over 2 to the n plus 1 times. Now we invert, that's 2 to the n, and this is going to be n squared. Okay. Now when we simplify this with this, we get a 2 down there. That brings us out a half, doesn't it? And that's going to be the limit as n goes to infinity. We're going to have n plus 1 squared up here. We're going to have n squared down here. Same argument we used right here. Greatest power of n up here is 2. Greatest power of n down here is 2. The limit, therefore, is the ratio of their leading coefficients. This is a 1. This is a 1. So we get 1/2 times 1, which is going to be a half, which is less than 1. So problem 26 is absolutely convergent. So I guess if we're going to go with the back of the books version of the way we're going to do this problem, the answer in the back is going to be yes. Yes. So that's 21, 26. We'll go ahead and do 28. Let's look at the ones that have been assigned. So I'll do 28 here. 28 is series n equals 1 to infinity, -1 to the n plus 1. Sorry, -1 to the n minus 1. Over 2 to the n divided by n to the 4. And the question is, does this converge absolutely? So we'll try the ratio test. So we'll take the limit as n approaches infinity, absolute value of, and this, if we're going to do the whole thing out, this is going to be -1, n minus 1 plus 1, right? Because that's going to be n plus 1, right? That's just going to be n. This is going to be 2 to the n plus 1 Down here we have n plus 1 to the fourth times. Now we invert n to the fourth. Down here we have negative 1 to the n minus 1. And we have 2 to the n. Now, when we do this and this, it gives us a negative 1. Here we have 2 to the n, 2 to the n plus 1. That leaves us just at 2. And here we have n to the fourth. And down here we have n plus 1 to the fourth. Now we can bring the negative 2 outside. Don't forget the absolute value. So when we bring it out here, right, when we bring it out here, it becomes a positive 2. And we have the limit as n approaches infinity. And once again, we have n to the fourth, n plus 1 to the fourth. So for the third time in a row, we have 2 times 1 greater than 1, right? So this diverges. Or no, to the answer in the back of the answer that the book asked us to find. So that's 28. Let's go ahead and do 29. We're on a roll here. This is going to be the sum n equals 1 to infinity, 10 to the n divided by n plus 1 times 4 to the 2n plus 1. All right. So we're just going to do the limit. We're going to turn all the n's into n plus 1s. So this is going to be the limit as n approaches infinity, the absolute value. That's going to be 10 to the n plus 1. This is going to be n plus 1 plus 1. That's going to be n plus 2, isn't it? And now we're going to have to put an n plus 1 in here. So we have 4 to the 2n plus 1. That's what they gave us. But we're going to turn it into 4 to n plus 1 plus 1. So that's going to be 4. That's going to be 2n plus 2 plus 1, or 4 to the 2n plus 3, isn't it? So that's going to go right here. Times. And now we just invert. So we have n plus 1. We have 4 to the 2n plus 1. And down here we have 10 to the n. Okay, here we go. Well, 10 to the n and 10 to the n plus 1 just leaves us at 10, it doesn't. Here we have an n plus 1 and n plus 2. So that n plus 1 is just going to stay up here. And that n plus 2 is just going to stay down there. Now we got to figure out what goes on with the 4 to the 2n plus 1 and 4 to the 2n plus 3. Well, there was a time in Algebra 1 or Algebra 2 where we taught you that when you divide, you subtract exponents, right? Isn't that what you do? So we have 2n plus 3 minus 2n plus 1, which is just 2n plus 3 minus 2n minus 1, or 2. So this becomes 4 squared on the bottom. Well, we have 10 over 16. So that comes out 10 over 16. The limit as n goes to infinity. And we have n plus 1, n plus 2, 1, 1. So we have 10 over 16, which is 5 over 8 times 1, which is 5 over 8, which is less than 1. So it converges absolutely. All right. Okay. That's probably enough of those. In problem 37, you get to do the ratio test 3 more times, right? 3 more times just to see when it's conclusive and when it's inconclusive. So hopefully
this helps you out with your homework in section 8.4.